Alright, today we are first starting with a leftover question from 3.6. I promised to solve this and I forgot yesterday. So we are first starting with this. What is this question about? We were solving nonlinear inequalities, a fraction inequalities. We solved number 3 and we were left with number 4 with multiple parts. It looks difficult, 4 parts, but no, all parts are the same. Only the direction is flipped. So if you figure out the first one, you can directly get B, C, and D. So there are two options you can answer this question. You can do it by logic. By logically, you can answer what kind of numbers make this thing less than 0 or equal to 0. And you can spot those values if you are good with properties of exponents and what happens when you divide positive number by another positive, etc. But if you have no clue how to do this biologically, you have to follow these steps. Okay? And I will follow these steps and explain the logic later. First, we need to get the right side 0 correct, and this is already the right side 0, so I don't need. So I'm doing part A. Step 1. Step 1 is clear. Step 1 is not necessary. Step 2. We need to set this into 0, set this equation into 0, and then solve it. So step 2, treat this as it's not an inequality, but it's just an equal sign, and solve this. And to solve any kind of equation, it's best if you factor it. Okay, so either you have a long polynomial on the numerator, no denominator, or you have a fraction. Always factor, factor, factor. Now I'm wondering, can I factor this denominator d squared plus 1? Can you factor that?
D plus 1, D minus 1?
Good. D squared plus 1 breaks as d plus 1, d minus 1. Agree? You're close, but we're missing something.
Plus 1, plus 1.
Right. This is true if you have a difference of squares of d and 1. If you have d and 1 squared with a difference in between, that's how you separate it. But unfortunately, this is a positive one. Actually, it's opposite. If you have a squares with a plus, this is not factorable. Not factorable. You cannot break it, never. So that's actually great. We can't factor this. All right. How about top? Top is already single. It's actually d, 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 d if you want to back factor it. It's not necessary. It's repeating same factors, d, 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 d. So you can just keep it as d. So in any case, this question requires no factoring. Then how do I set this and solve it? How do I set it and solve? How do you solve this? Yeah. Usually, if you have a denominator, you multiply both sides by denominator. Put a parentheses around it. It has multiple parts, like d squared and 1, 2 parts. And they do cancel, of course. That's why we are doing it. Now we have only d to the 4th raised to the 0, raised and set it into 0. If a number raised 4 times, 4th power, and set it into 0, what number can it be? What is d? Or technically, you are taking 4th index square root of both sides. These two cancel. What is 4th index square root of 0? Root of 0?
0.
It's 0. This is the puzzle question. What number multiplies itself 4 times? You have a mysterious number multiplying itself 4 times and becoming 0. It has to be 0. Okay? Alright, so you have only one. Why are we doing this? To find out boundary values, boundary points that creates rooms on the real line. We are going to create rooms and decide pluses and minuses, remember? So I found one so far, and I need to search one more location. I need to search if this function breaks down and becomes undefined, fails sometimes. So do you think this function can become undefined? Usually fractions become undefined. Remember, this fraction became undefined. When did this become undefined? -5 is the bad guy. So it was a boundary value for us when we were dealing with this. Can you find such a number here? You square it and add 1, it's gonna make it 0? No? Are you sure? Yeah. Because when you square any number, either negative or positive, they turn positive. This is always a positive number. When you add 1 to a positive number, it becomes more positive, right? So can it ever drop to value 0 then? Impossible. So this thing is never becoming undefined. So you have only one boundary value on this line, which is right in the middle. And it makes my function 0, so I will put a little circle here. I will only check, there are 2 rooms to discover them. Left room and right room. We're going to check whether this function is positive or negative here by simple testing. Test a value. Test the something. Test the something else. What d value you want to test? Before 0. Come on, what's the -1? All right, please somebody substitute -1 and tell me what's this ratio is, positive or negative? Positive, because when I raise a negative number to the 4th power, even exponent, it's positive. This is positive. Add 1 more positive, divide 2 positive things. It is of course positive. Positive, positive, positive. How about 1? If you enter 1 here from the other side, 1 to the report, 1 squared plus 1, everything is positive, ratio is positive. So this function doesn't flip signs, no sign change, it's everywhere positive. And what is this asking now? Who can translate this into English? What does this mean? When the function is, what is this? Less than or equal to, the other way to say this is negative. If it's less than or equal to 0, negative or 0. Right? 0 equal, so we need to include that or negative. So tell me, according to this table, when, for what values I need to take here, cover that room, I don't know, you see a minus sign. Which room does have a minus sign? None. So it never becomes negative. But does it ever become 0? Yes. Where? At x equals 0 or d equals 0. So there is only one solution for this case. It's only 0. That's it. Now, am I solving the right question though? No, but I got away with it. I got it correct. Because look, they just changed this into 6. Instead of 4, I have 6. But any of the steps, does any of the steps change? No, it's the same steps everywhere. Imagine you have 6's here. You're repeating over and over the same thing, okay? Okay, next question is, when does this thing become negative? Certainly negative. Not even possibility of being 0. When? Never. How do we say never? Do we have a bottom for it? Never? I don't know.
Circle with a line.
Yeah, empty set. Good. Next, when does it become 0 or more? When does it become either 0, it becomes 0 at 0, or positive? to the left of 0, to the right of 0, and at 0, it satisfies all this, right? Correct? Yes, entire real line, which is negative infinity to infinity. And when is it certainly more than 0? When is it certainly more than 0? Not possibly 0. We want to avoid being 0. So it's positive on this side of the line. On that side of the line, how about right in the middle? Shall we count this one in? No, it says don't take equals 0, so we will exclude. There is a hole here. Take the right side and left side and unite. We will take the left side first. Left side is negative infinity to 0. And the right side is 0 to infinity. And we unite both pieces. That's why we exclude right the middle value 0. Okay? That finishes that forgotten question in 3.6. Now we're back to 4.1. Any questions, Jerry?
No.
Okay. We started 4.1 yesterday, and we were about, which question are we? What's this? 4.2. We learned about inverse of functions. And to be invertible, a function must be one-to-one first. We discovered one-to-one testing methods by vertical line test. No, it wasn't called vertical line test. It was called horizontal line test. And then a direct definition method, which was cumbersome, but it works. And now if we know two functions given, we can test whether they are inverse of each other by composing them. That's what we figured, and did 2 questions. And finally, we found inverse of a function, this one. And we are going to do one final question here, which is a very comprehensive question. It explores all the properties of inverse functions. And very enlightening, very comprehensive question because it checks domain and range relations as well. So it has many parts. Okay? Alright, first thing we're going to do is very essential part, graph this thing. And this graphing method requires some techniques from section 2.6. What was in 2.6? It's transformations of graphs. Remember, I asked you to memorize 6 graphs, main function graphs, and one of them is present here. Which one? What is it called? Name of that graph? What's that? Square root x. You guys remember square root x? Was this, right? Square root x. Agree? No. This is x squared. Wrong one. This is parabola. It doesn't have a square root. Oh, which one was it? How does it work? Was this correct? Agree? Starts at 0. Are you sure it doesn't have a left side? Does it have a left side? Can you compute a negative number here? No. Square roots doesn't work with negative numbers. But this one will do, I think. No, won't do. Sorry. Won't. Well, this is root x. I need x minus 2. I bet that minus 2 is a shift. What kind of though? Up, down, left, right, stretch, shrink, reflection. It's a right shift 2 because it's affecting directly x values. It's not outside on the end. It's directly changing x, horizontal shift to the left, right. That's right. So all you need to do is move this thing 2 units to the right. There you go. And put a minus sign now. And what is this starting value then? If I shift from 0 to right, it is 2, 0, right? Correct? Alright. That's it. We graphed it. How easy is that? If you know your transformations, yeah, it's easy. Otherwise, you need to make a table and test x values, connect dots, a lot of work. Okay, second, is this function one-to-one? What do you think? Is it one-to-one? How do you test it? Easiest testing method is if you have the graph, which you do horizontal line test. Otherwise, you need to do definition, f of a equals f of b, and you need to get to a and b. Too much work. You have the graph, scan it with horizontal lines, see if you cross it more than once. Can you ever cross it more than once? Can you? No. This is a good one. It's a one-to-one function, yes. All right. Yes. Tell me how you decided that by horizontal line test. Write the domain of f in interval notation. Look, these are all past information. How do you guys find domain of a function if you're lucky to be given the graph of it? Otherwise, you need to look at this and see when it's positive, set inequalities, etc. But when you have the graph, all you need to do is, what do you need to do? How do you determine domain? Yeah, this is going to be tricky. Yeah, what is the domain? Describe me how you found it. You just push this down to x-axis, okay? When you push this down, all these points fall to a region. What region? It's this region, starting here and going all the way to infinity. So it is q to infinity. Okay. Okay? How about range? Austin? 0 to infinity. You this time press it to the y-axis. Push it to the y-axis and the points fall this direction now. And they fill up all the space about y-axis, about x-axis on positive y. It's gonna be 0 to infinity, right? 0 to infinity. All right, here comes the algebra part. Find F inverse. Find its formula. Part B requires some steps. And those 4 steps from yesterday. First off, we change f of x by y. So where is f of x? Here. I call it y. What do we do next? Second, Second.
Interchange x and y.
Yep. We make all y's x, all x is y. You see the change? This became x, this became y. Everything else is the same now. That's step 2. Step 3, what is step 3? What?
Solve for y.
Solve for y. We need to isolate y on one side, either right or left. But to isolate y, I need to get it exposed. It's hiding under a square root. I need to get that square root out of my way. What's the right weapon to cancel a square root? Square. So we will square both sides. Put the square to those both sides. There you go. And I have only x squared on the left now. And on the right, these two cancel. And I have almost y alone, except 2. Cancel a 2. I add both sides 2, and we're done. We have isolated y, but in the wrong side. I don't like the right side, so how do I fix this? Just switch the sides. Put y on the left and everything on the right. Okay? We're done. You just discovered f inverse. All you need to do is step 4. Call that y f inverse is actually here. Let's call it x squared plus 2. Alright. I want to mention something. We are wrong. We are not correct 100%. It's kind of incomplete. Why? What's going on here? Let's. Let's graph this, right? Clean this. Can you guys graph x squared plus 2? X squared is a parabola U-shaped. Plus 2 is going to move it 2 units up. So 2 units up, a parabola. This is it. That's it. There you go. You got it. Alright, I can't go more up. What? What's wrong with this picture? Go back to yesterday, very first slide. What did I tell you about functions and their inverses? What kind of property their graphs satisfy? When you put a y equal x right between those two graphs, y equal x, that line between x and y, right in the middle, these two graphs must be symmetric. Right? Must be symmetric. So what's going on here? Where am I? We did all this, right? Okay. If I put that line, where is my line? Y equal x. Here we go. Here's y equal x. Symmetry of this curve is this thing. Do you see that? I bended this backwards here, but this side, this point showed up here. These are symmetric points. And this part, however, this created another branch underneath my original curve. As a matter of fact, this function is not one-to-one. I can't even find its inverse. So what happened here? This is what happened. Actually, I let you square both sides of the equation whenever you get a chance. I let you square both sides, right? Where did we square? We squared here. But squaring actually is the dangerous move in solving equations. When you're squaring, you're actually doubling your solutions. You're creating an artificial piece like this. You have x equal 2, right? When I square both sides, I get x squared equals 2 squared 4. And when I go back and take square root, I get what numbers make square 4? Plus and minus. Look what happened. When I squared a simple equation and try to come back, I get, instead of a unique solution 2, I get double solution. This is exactly what happened here. Instead of a one branch I'm supposed to get, I got 2 branches. So one of them is extra, and we have to cut it out. We have to mention it here and say one of the pieces is fake. So which piece are we going to avoid and how? I know that this piece is extra because it's not symmetric to original. So I need to go clean this part, and the corresponding piece, this one must go. But where was this piece? It was about negative x values. So I need to take away negative part and say only this is true for positive part, okay? So here is the lesson we got. When you were finding f inverse, if you squared both sides, you need to limit your x values for the right piece. You need to go say it here, okay? So we need to say that here for x values greater than or equal to 0. This actually explains both parts. That's why it says why we need to put x greater than 0 here, because of my explanation earlier. We squared, we messed up the equation. We created a double piece. Alright? Make sense? Alright. Next, graph f inverse. I already did. This is f inverse. Just the right piece, starting at 2. Is on it. Okay, we did that part too. Next, write the domain of f inverse. You can cheat here actually, if you observed this before. Domain of f inverse. Look, what is the domain of f inverse? It's these values. It's actually the range of f. So what did you find for range of f? Where is 0 to infinity? So domain of this guy will be the same. Look, if you don't trust me, literally press this down, and see what domain you get. 0 all the way to the right infinity. Same as range of this guy. Range of f, domain of f inverse, match. Alright, guess how I'm gonna find range of f inverse. Yeah, you can press this to the left, and watch out for values, which is 2 to infinity, or you can cheat from f. Range of f is the same as domain of f. Range of f inverse is the same as domain of f, which is 2 to infinity. Okay? Now, any questions? Are there any questions? No? You're lying. Come on. So this is 100% clear? Yes?
Did you say f is going to be the same as e? Or, yeah, is f going to be the same as e answer-wise?
Part F I explained E and F at the same time here, okay?
Okay.
But let's see how it's demanded on Connect Math. I don't know what requires there. Let's take a look and answer these quickly. Alright, which one was the right picture? It was D. Check. Is F in 1 to 1? Yes, it is. Domain of F is 2 to infinity, we found. Range of F was 0 to infinity. Alright, we found F inverse as x squared plus 2. But x must be picked more than 0 only on the positive side. Explain why this restriction was necessary here, because f of x values, actually, that piece, why we don't have the negative side here? Because we have only f of x values. Original f doesn't have this lower piece. So f of x values are always positive. We don't have anything underneath x. So we don't create this piece because we don't have anything underneath. So negative values are omitted. We omit this part. So only positive. F of x is positive. That's why we are doing that. Okay? And we plot f and f inverse on the same picture, not this. There must be y, they must be symmetric with respect to y equal x line. This doesn't look symmetric. Only part B, right? Part B, x squared plus 2 is this guy, and root x minus 2 is that guy. And two more. Domain was the range of f, which is 0 to infinity. And range was domain of f, which was 2 to infinity. Okay? Look, every time I enter a right answer, it's saved automatically. You don't have to submit or anything. It gets full credit once you get the right answer. Well, I don't have any credit, people, because I haven't done anything in this set, right? I didn't answer nothing yet yesterday. But I want you to again submit it anyway, so I can see your score. If you don't see your submit, your score is saved, but I don't see it. That's the problem. So if you feel you're done with it, hit submit, okay? So I can have your grade visible. I have only 9%. Okay, that's good. Okay. 4.2 is coming up next, which is exponential functions. If you don't have any further questions. Alright, what is exponential functions? Let's first take a real life example. And this is really interesting. I have heard a story like this with a king and a farmer. I think farmer did a favor to the king, and king wants to reward him, and he said, "What do you want from my treasury?" Okay, and the farmer said, "Oh, you like chess? Okay, on your chessboard, I just want for every square on your chessboard, I want a bucket of grain, wheat." Okay, grain. Oh, king said, "Oh, it's okay. It's just bucket per each square." No, he said no. But every next square, you need to double the bucket. And the king thinks, "Oh, double of a bucket and 4 times a bucket. It's no big deal." But when you reach to the last square on the chessboard, every time you're doubling the buckets, you run out of all the wheat in your country. It's so growing so fast. So this is a very similar example. So you got a job offer, but I'm offering you two options for pay. Option one, I'm offering you a direct payment of $1 million after 30 days. You do the job, you get $1 million, that's it. Or I offer you 2 cents on the first day, and then I double your salary for each day you're on the job. So which offer would you take? Would you take $1 million or would you take 2 cents each day? Don't cheat, come on. Yeah, table explains that 2 cents is a better deal. How come? You're getting paid 2 cents on the first day, but every day it's doubled. Next day you get 4 cents. Third day you get 8 cents, 16 cents. After 2 weeks, you're still making $163. Seems nothing compared to $1 million total pay, right? But look at 3 weeks. After 3 weeks, you're still making 20,000. But it really picks up in the last week, unless you're fired. Yeah, in the last week, everything is doubling. And on the last day of your job, you're getting a $10 million check for that day. So in total, you're probably making 20 million or something. When you add up these things, almost 20 million comparing to 1 million plan. So this actually demonstrates the power of exponentiating. Power of exponentiating, okay? All right, what is going on here? You are computing powers of 2. You put 1 here, it's 2 to the first. You put 2 here, it's 2 to the second. You put here 30, then you're getting this amount. It seems like, come on, just 30 and 2, small, abysmal numbers, 2 and 30, weak numbers. They come in the right place, they make huge power, huge number. So, story we got here is exponential functions grow very fast. So most people compare these with this. What is the difference? This grows as well. Like you put 3 here, 9. You put 4 here, 16. You put 5 squared is 25. 49. 100. If you put 10. But this is growing, but comparing to this, 2 to the 10, 2 to the 10 is, that's cents, that's why it's not 10,024, 2 to the 10. 1,024. Right, is that right? This is 10 squared is only 100. You see, even at 10, this guy beats the other one. 2 to the 10 is bigger than 10 squared. This is really fast, rocket launch growth. This 1x squared is, however, some growth, still fast growth, in my opinion, not as much as that one. So after experiencing that, let's make the formal definition of exponential functions. It is numbers on the base. There should be a number on the base, but on the power you must have a varying object, variable on the top. That's important. When I ask an example of an exponential function, people give me this. This is not exponential. Yeah, there is an exponent and a base, but they're in the wrong spot. Number on the top, variable on the base. This is a power function, power or polynomial, we call it. But this is, base is fixed, never changes. Top is changing, okay? Again, not exponential, 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 not. How come? Why is this not exponential? You know why? The bases are not allowed to be negative. Bases are not allowed to be negative. This is why. Explains here in the mistake. Most people think negative bases are okay, such as I take a negative base raised to x. Imagine x is 1 over 2. And power 1 over 2 means square root. Can you take square root of a negative 4? Can you take square root of any negative number? No. That's why we avoid negative bases. Actually, I like them, but it's look exponential, but we sometimes cannot compute them sometimes. That's why we avoid them and don't call them exponential. No negatives. What's wrong with 1 to the x? Because 1 raised to any power is actually just 1 itself. The kind of x disappears, no exponent. So we don't technically call this exponential either, okay? So what's the story we got here? You can pick any wild number on the bottom, any number, fraction, ratio, radical, square root, or 3, whole number, as long as it's positive though, positive, and not 1, don't take 1. Can it be 0.0001? Sure, it's fine. How about 0? They didn't mention 0, right, anywhere. What do you think about 0? 0 doesn't count either, okay? So 0 to the x, as long as this is not 0, is 0. Oh, by the way, this is weird. 0 raised to the power 0 is undefined. If any of you guys are going to go for calculus course, we will do this a lot there. 0 raised to the first 0th power is undefined. Don't ask me why now. Just keep informed. It's coming up. Alright, are we good? Again, how do I know exponential functions are what they look like? Look at this word. Exponent. You expect some exponents. And variable exponents especially. Alright, first thing we're going to do is we're going to take a look at their pictures. We have example of 2 different exponential functions here. First one is 2 raised to the power x. The other one is 1 over 2 raised to the power x. What's the difference? 2 is considered to be a big number. Anything more than 1 is considered big. 1 over 2, it's less than 1, is considered small. And somebody already computed several x values and inserted this x and take a calculator and compute. You get 1 over 8, 1 over 4, 1 over 2, 1, 2, 4, 8. You plot those, we see a function going up. When you, from left to right, you are climbing up. It's a very steep angle, huge, fast growth. But when you enter those values into the 1 over 2 to x, you start big, get smaller and smaller, and tiny little bit number. So you are going down, you're sliding here. So when does this happen? If you have a number on the base less than 1, it's a sliding picture from left to right. When a number is big, you're going up. Alright, I want to give you a good fact here. How do you think they computed this 2 to the x at 3? This is 2 to the minus 3. How did they arrive this answer? I wonder that. Do you guys know this trick? You cannot compute negative exponents of numbers directly. You need to flip them to positive. How? How do you flip them? The technical name for this is called reciprocal. You put this whole thing under 1 and change the sign of the exponent to opposite. Okay? And look what happened now. 1 on the top, this is triple 2. 2, 2, 2, that's how they got 1 over 8. Okay? Understood? Sometimes you may see that negative exponents in the bottom already, in the denominator. Now how do you compute this? 1 over 2 to the negative cube now. Do you know how?
They're the one on top, it's just 2/3.
What's that?
It's just 2/3.
Yeah. You can move it to the top as long as you flip the sign. So this is reversible. You can, if you want, pick it to the top, move it to the top by flipping sign. So I'm flipping the sign again, it's 2 cubed. 1 over 2 to the negative third power was 2 to the positive 3. It's actually 8. Okay? Make sense? So whenever you need to change a power to the top, you flip sign, or anything to top to bottom, you flip sign again. Sign of the exponent only. All right. Any questions on this? All right, then graph 7 to the x. Should be 2 seconds. What is it gonna look like? Just describe it. Is it rising or sliding? Decreasing or increasing? Increasing. This is going more than 1, right? So that's it, I'm done. Well, technically you need to be testing several values, okay? I know what it looks like, but this is what you're supposed to do actually. Set some x and compute y values by 7 to the x, such as -2, -1, 0, 1, 2. When I put this, it's 1 over 49, 1 over 7, 1, 7, 49. Okay? How did I get 7 to the negative 2 again? 1 over 7 squared first, and 7 times 7 is 49. That's how I got it. But how do you plot this number? It's, I think, almost 0.02 something. So change it to decimal and plot if you wish. So let's see how small this number is. I must be really close. So I'm going to back up this one and go really close on this side quickly. Here. And this is like -2. And this value is like 1 over 49, for example, okay? 0.02 almost. All right, and mark this value, etc. So you're supposed to get all these values like that and connect the dots. But I already know how it looks like, right? Okay, one question though, or one point I want to make here is, no matter what base you have, this center value 0, 0 will never change. Do you know why? Look, if this is 2 to the x, 5 to the x, 10 to the x, 7 to the x, no matter what you enter on the base, that base raised to the power 0, this is a fact. Any base raised to the power 0 is always 1. This point is always same in no matter what kind of exponential function you have. You see this point? They meet each other here. Every exponential function meet each other there, unless they really change it and added some numbers. Unless you see numbers added or subtracted on the end. If they are only raised into a base with some x, they will meet right here. And then they will quickly go up or slowly go up. It depends on the power base value, but this is one fact. By the way, all exponential functions approaches to x-axis. So what do we call this x-axis to be? We have a special name for it. If your line on the left end of your curve on the left end gets almost touchy, but not really touching, on the right or left, if it's getting closer to a horizontal line, we call that line to be asymptote, horizontal asymptote. Every standard form exponential function has y equals 0 or x-axis as an asymptote. All right, they want us to graph this, but I believe you know what its graph look like. 1 over 3. 1 over 3 is going to look like, I'm going to put it right on this one. Which button did I touch? Oh, we're out of time anyways. Okay. Oh, there we go. All right, let me finish this. Let me finish that. So just describe me, what does this picture look like? Is it also going up? It will be going down picture from this way and moving up on that side. But it's going to be a slower pace than this one, so it's going to grow slowly on this side. Like that. Okay? They will meet each other. Alright, we'll see you tomorrow. We'll finish this section on tomorrow.